Had our notes, and so a quick review from last Friday is I showed you this image. So electron density. So this image is showing you that, hey, where there's a lot of shading, where the density is great, that's where we're more likely to find an electron. And where the shading is lighter, that's where we're less likely to find an electron. So scientists have a pretty good feel for where electrons are going to be found the majority of the time. And so they call those orbitals. All right. So orbital is a location where 2 electrons are probably going to be found at any given point in time. And then I like to talk about, the Heisenberg uncertainty principle. Like when the fan is off, we know exactly where the fan blades are. It's easy to see where the fan blades are. But when we plug the fan in, we see this like big cloud, right? And we don't know at any point in time, we don't know exactly where the fan blades are. We know they're somewhere within that cloud, within that blur, but we don't know exactly where. That's like electrons. We know electrons are to be found somewhere within that orbital. We don't know exactly where. So our job is to say, hey, this is where electrons are likely going to be found. And based on that information, we can get a pretty good feel for how an atom is going to react, how it's going to bond, the shape of the molecules is going to form as a result. And those are all things that we'll talk about once we get into next unit, Unit 5, and then Unit 7, we'll get into our molecule unit where we look at shapes and structures of molecules. So think of electrons moving like fan blades when the fan is on high speed. They're somewhere in there. We don't know exactly where, but we know they're there. Or you can think of an airplane propeller. All right, and then Friday we talked about every electron has an address, and it's made up of 4 parts. Like your home address is made up of 4 parts: the country, the state, the city, the street. We get more and more specific as we go on. Well, an electron's address is made up of 4 things, 4 quantum numbers. And so I want to do a quick review. We looked at the first 3 quantum numbers on Friday, and I want to talk about quantum number 4. So on page 9, we talked the first part of an electron's address. The first quantum number is called the principal quantum number, and that tells you which energy level the electron is found in. All right, so 1 is closest to the nucleus, 2 is farther, 7 is the farthest away. So 1 through 7, every electron will have an address. The first part of the address will be 1, 2, 3, 4, 5, 6, or 7. The next part of electron's address is the sublevel. All right, so the next number, and I didn't give you the numerical values that we will do that in the future, but the second quantum number will basically specify, is the electron found in the spherical region, an S, dumbbell-shaped region, one of the P's, or is it found in a D, or is it found in an F? All right, so first number, principal quantum number, which levels is it found in? Second quantum number will tell you, is it an S, a P, a D, or F-shaped region? The third quantum number will specify which orbital is found in. That's called the magnetic quantum number. So if we go back here and look at the P's, like there's 3 different P orbitals. So to say an electron is in the second energy level P sublevel, you need to specify which orientation in space, which orbital is it found in. Is it found in this one? Is it found in this one? Or is it found in this one? So that third quantum number will specify like which orbital was found in within that sublevel. And then finally, new information here. Fourth quantum number is the spin. Electrons are little tiny pieces of matter, and they do have a spin. Some electrons are spinning clockwise, and some electrons are spinning counterclockwise. And this is the importance of the spin when we get into orbital diagrams. But just know when we start drawing orbital diagrams, which you did a little bit on ChemQuest 4B, you saw up arrows and you saw down arrows. So basically an up arrow represents one direction spin, which we'll call clockwise. And a down arrow represents an electron spinning the opposite direction, counterclockwise. And so for the fourth quantum number, we either assign a number of positive 1/2 or negative 1/2. So positive 1/2 represents a clockwise spin. Negative 1/2 number for the fourth quantum number represents a counterclockwise spin. Some more to come on that in the future. So big thing today, 2 big things today. First thing is filling out that table, filling out the chart. All right, so at the bottom of page 10, this is where most of our note-taking time is going to take place today. And this is very helpful, I think, for a lot of people. So one thing I want to point out here, this is the energy level. All right, so we got the first energy level, second, third, fourth. Now there is a 5th, 6th, and 7th energy level, but I didn't want to make the chart too big. So we're going to stop after 4 because what we see in the 4th will be the same for the 5th and so on. So the first energy level is the smallest, and it's already completed for us. The first energy level only has S sublevels. Just like the boarding house only had a sunny room on the first floor, electrons can only be found in the S-shaped homes in the first energy level. And if we go back and look at our diagram, for the S's, there's just one sublevel. There's one orbital making up that sublevel. All right, so notice there's one orbital. That one orbital can hold 2 electrons, and so the maximum number of electrons that can go in the first energy level is 2. And that brings us to the second energy level. Now, every single energy level will have an S. All right, so the second energy level will have an S, a spherical shaped region where electrons would go. The third energy level has an S sublevel, which has a spherical shape where electrons can go, and so does the fourth and the fifth and the sixth and the seventh. And so I'm going to color code this. So if you have some colored pencils, it might be helpful. We'll just fill in that first line for each energy level with the same information because it's identical. The only difference between a 1s and a 2s and a 3s is the size, the distance the electrons are from the nucleus. And I'll show you a quick animation once we're done with this chart. All right, once you fill in the S's, if you are going to color code the system, grab a different colored pencil. I'm going to use blue for my next one. The second energy level is bigger, and so the second energy level also has P's. Right? There's 2 S's and 2 P's. Second energy level S, second energy level P. And if we go back and look at our chart or pictures, circled in blue are the 3 different orbitals, the 3 different regions that make up the P. So there are 3 orbitals, 3 electron bunk beds. Each one can hold 2 electrons for a grand total of 6. So the second energy level is bigger, has P's. Third energy level has P's. The fourth energy level has P's. The fifth, sixth, and seventh energy levels also have P's. And note here, our second energy level is maxed out. There's only S's and P's in the second energy level. So if you add 2 and 6 together, you get the max number. The max number of electrons that can go in the second shell. Second energy level is 8. All right. Third energy level is even bigger. So there's even more room for electrons. So there's S's, 3 S's, there's 3 P's, and then there's also room for the D sublevel, the D orbitals. And if we go back and look at our chart diagram, look, there's 1D, 2D, 3D, 4D, 5D. There's 5 different types of D orbitals. Each one of those can hold 2 electrons. 5 times 2 is 10. So there's a 3D, there's a 4D, there's a 5D, there's a 6D. So every electron level is bigger, it can hold more electrons. And so for the third energy level, we have 3s, 3p, 3d, 2 plus 6 plus 10. The maximum number of electrons that can go in the third energy level is 18. All right, and the fourth energy level has room for even more electrons. So the fourth energy level is the first energy level that can have f orbitals. And there's 7 different types of Fs. Each one can hold 2 electrons. So 7 times 2 is 14. And if we add together the totals for the fourth energy level, 2 plus 6 plus 10 plus 14 is 32. So there's room for up to 32 electrons in the fourth energy level, and that is it. So those are the magic numbers. 2 can go in the first, 8 can go in the second, 18 can go in the third, 32 up to 32 can go in the fourth. You're thinking, all right, that's not too bad. So let me show you a quick video clip. And there's no sound to it, so I'm not going to turn my sound on. And this is a quick animation showing you how the S's and the P's fit together. So neon has 10 electrons. So this is going to show you where neon's 10 electrons would go. So we always fill the electrons in the same order. The first electrons always go in the 1s. And one thing I want to point out here, where the axes intersect, this is my nucleus, right? The nucleus is right here where my mouse is hovering. So the 1s is this spherical region, and only 2 electrons can go here. So the first 2 electrons will always be found in this shaded region. Once 2 electrons are there, the next electrons go in the 2s. So look at the 2s, same shape, right? S, it's spherical, but it's part of the second energy level. And so second energy level electrons are farther away from the nucleus. It's the same shape, it's farther away, 2 electrons to go here in this shaded region. And then we'll add electrons to the 2p. Notice how these intersect. They're not mutually exclusive from each other, but they are constantly overlapping, intersecting. So 2 electrons to go here in the 2p on this axis. 2 electrons to go here in the 2p region, a dumbbell-shaped region on this axis. And then there is a third orbital for the 2p that falls on a vertical axis. And the final 2 electrons could go here. All right, so neon has 10 electrons. This is where the first 10 electrons will always go. All right, so we can predict where they're going to be found. And that will allow us, like I said, to predict how they're going to react and the shapes of the molecules that they're going to form. All right, so back to the slideshow. Let's look at this. All right, so writing electron configurations. This is what it all comes down to. This is the point of the unit. What are the addresses of the electrons? When you write an electron configuration, it's showing where the electrons are found, which sublevels are found, and how many are found there. So remember, ChemQuest 4B, the first 2 pages, this looks like the manager code, right? We could represent where the borders are within the boarding house by using the manager's code. Well, this translated to atoms. This is where the electrons are found at. And I'm going to read the information below this. Number 2, it says, when writing electron configurations of elements, we must follow the off-bow principle. The off-bow principle basically means to build up. This principle states that when an atom in its ground state, normal state, not excited, the electrons will fill up the lowest energy level sublevel first. And for the next couple of days, we can use this flowchart. Now, I said the next 2 or 3 days here in our notes, but you know, everything we do here is open notes, and the test will be open notes. So you can always use the flowchart. The flowchart will be your best friend as you start out here. So bromine, if you look at your periodic table, bromine is element Br, it's element 35. So we can assume there's 35 electrons because there's no charge. And so this is where bromine's 35 electrons will be found. Now look, 1s2, that little 2, this superscript tells you how many electrons are in the 1s. That means there's 2 electrons in the first energy level S region, 2 electrons in the second energy level S, 6 electrons in the second energy level P, 2 in the 3s, 6 in the 3p, 2 in the 4s, 10 in the 3d. The last 5 electrons would go in the 4p. If I add up all my little numbers, my superscripts, that'll tell me how many electrons are there. So 2 plus 2 plus 6 is 10, plus 2 plus 6 is 18, plus 2 is 20, 30 plus 5, 35. So every electron is accounted for. So let's look at the flow chart now. So for every element, we're going to follow the flow chart. And it says, note at the bottom of the flow chart, it says, note, even though the 3D electrons belong to the third energy level, the 3D electrons have a little bit more energy than the 4s electrons. So that means that we're going to fill up the 4s, the fourth energy level S, before we add electrons to the third energy level D. Therefore, there's exceptions to the rule, and we may or may not look at any of the exceptions to the rule just because we don't want this unit to last forever. So I think we'll probably just try to stick with the mainstream ones and not look at the couple of known examples or exceptions to the rule. So let's look at number 3 at the bottom. It says, write the longhand, that just means your normal configuration for gallium. All right, so example 3 says, write the electron configuration for gallium. The first thing I do is look at the periodic table and say, how many electrons does gallium have? Well, gallium is element 31. So gallium has 31 protons, 31 electrons. So we need to find the locations of gallium's 31 electrons. So we're always going to start here, off-bow principle. We're always going to start here and then work our way through the flow chart and fill it up in the same sequence every time. So the first electrons for gallium go in the 1s. And how many electrons go in the s? What's the maximum number that can go in the s? Yeah, 2. So first 2 electrons for any element would go in the 1s. Once the 1s is filled, I wouldn't cross these out in your notes because you're going to need to look at this. I'll cross mine out because I can erase it easily, but don't cross them out in your notes. Once you fill out the 1s, go to the 2s. 2s can hold 2 as well, right? So once we put 2 electrons in the 2s, we keep moving on. The next one is the 2p. How many electrons can go in the second energy level P? Max number is 6. Yes, 6. So 2p can hold 6. And then after that, we go 3s. And because it's an S only has one orbital that can hold 2 electrons. So we're up to 12. We have 19 to go. After the 3s comes a 3p. And the p can hold up to 6 electrons. So now we're up to 18. After that, we go 4th energy level S. And because it's an S, it maxes out at 2. Now we're up to 20. And then next up, we go back to the 3rd energy level. We go 3D. And 3D, how many can a D hold? Not 2, not 6, but 10. Yes, 10. So Ds can hold 10 because there's 5 orbitals, 2 electrons each. So now we're up to 30. We got one more electron. And this is the number one thing that people will do incorrectly is they'll say, oh, 4p can hold 6. So this is how many electrons there are. Yes, the p can hold 6, but we only have 1 electron left. So we would end our electron configuration with 4p1. There's only 1 electron in the 4p. Even though it can hold 6, there's only 1 left, so it ends in 4p1. So if you add up the little numbers, it adds up to 31, so you know you're done here. So every single element that you do is going to follow that same path, the same flow chart. All right, so the electrons always follow the same sequence. So really, the only thing you got to do is keep track of the electrons, so you know where you're at. And then the very last orbital that you fill up, you got to remember how many is actually there. You can't just put how many is the maximum number. You got to figure out how many is left over, how many is actually there.